SwayamPrabha. Digital India. Educated India.
Okay, so let us continue our discussion in this module 5. So today we are going to discuss about formability testing of sheet materials. Okay, so in the previous section we introduced the concept of forming limit curve and what happens during necking process, specifically in the the biaxial stretching region, that is in the first quadrant, is what we have seen. And we will introduce that again, and then we will go ahead and see what are the different formability tests available to estimate the formability or forming limit or deep drawability or stretchability of sheet materials. So in this module we are going to see only formability testing of sheet metals. So let us introduce this forming limit curve again. So what is this forming limit curve? This forming limit curve is nothing but the curve which indicates onset of local necking in both the regions, that is in the first quadrant and in the second quadrant, and it is nothing but the locus of limit strains. We introduced epsilon 1 star comma epsilon 2 star in the previous section. And if we get this data for different values of alpha or beta, right from, let us say, on the left hand side extreme to the right extreme, if we get, so negative minus strain to positive minus strain, if we get, okay, so then if we connect all of them, that is nothing but your forming limit curve. That's what we have seen. So this star, whatever I mentioned here, are forming limit strains. So we said that it is a material property. So unless otherwise you change something in the material, it is not going to change, it will remain same. And we have also seen that it is useful for various reasons. One is you need to get the failure diagnosis of the sheet grades, quality of sheet. If you estimate it, then it will be useful. Okay, so you want to select a particular material, sheet material for a component, then this will be useful. You want to decide the process conditions like lubrication or lubricants, forming temperature, strain rate, whether it is sufficient to form the component, then this forming limit curve can be used. So before we understand the different methods of formability evaluation procedures, okay, so because we introduced a forming limit curve, let us discuss one or two important methods through which we can evaluate a forming limit curve. So let us discuss that. Then we will go ahead in discussing about other formability tests. So that's why I given a topic today is FLC evaluation, forming limit curve evaluation, and other formability tests. So forming limit curve or formability, I think we understand the meaning of that. It is nothing but the ability of the sheet material to get converted into a particular shape without any instability, without any necking in that, without fracture. That's the meaning, and forming limit curve can be used to evaluate that. So one important method, procedure or test to evaluate forming limit curve of any sheet material is called hemispherical dome test. It can also be called as limiting dome height test. So hemispherical dome test, as the name suggests, you are going to have a punch, okay, which is of hemispherical in shape, okay, and so naturally there are tools available for that. Okay, so you can install the tools and then you can deform the sheet with the help of punch setup, and then you keep deforming the material, the sheet, as per the procedure that we are going to describe until necking occurs or fractures. Whatever is possible for us to stop, we will do that. Okay, so then it is called as a limiting dome height test. So you are going to get a dome shape and that will be limited because of formability of the material. So you call that as limit minimum height test. Okay, so in short it is called as a LDH test. So it is an evaluation procedure or test for metal sheet deformation capability using an experimental setup having a hemispherical punch deforming a sheet with circumferential clamping force sufficient to prevent it from sliding or pulled into the die cavity. So we will see that. So in this test procedure, the procedure is actually very simple. Okay, it's not that very complex. So you keep the sheet, you hold the sheet, okay, with the blank holder. Okay, so you keep the sheet on the die, you use a blank holder and hold it, and then punch will come separately and push the sheet inside the die cavity until necking happens or fracture happens. And then you take the sheet out and you measure the epsilon 1 and epsilon 2 near neck region. That becomes 1 point in this particular curve. Okay, that becomes 1 point in this particular curve. So like this, you change a strain path by one particular way. You change a strain path, betas, predefined strain paths, predefined betas. Okay, that's why we say beta. You can imagine why it is predefined, because it is alpha naught and beta naught, we said, isn't it? So during the course of deformation, during necking, it can change, but it's a predefined strain path. Okay, you get limit strains in other betas. So by changing the strain path, so procedure is very simple. Okay, and in one sentence you can tell the entire procedure in this way. Okay, so one important issue here is the sheet generally should not slide inside. Okay, so sheet has to actually stretch below the punch. That is the main thing here. That's why we mentioned that with the circumferential clamping force or blank holding force, you can say, sufficient to prevent the sheet from sliding or pulled into the die cavity. It should not draw in, it should not be pulled in. So it has to be clamped tightly like that. Okay, so this is nothing but a procedure for constructing forming limit curve of a metallic sheet by using a hemispherical deforming punch. Okay, and generally this test is available for all sheets which has got this particular thickness of the order of this 0.5 to 3 mm thickness. Okay, so before we do that, there are some important definitions I thought it will be useful for us. One is a forming limit curve. We call it as FLC. It is a curve showing the strain levels beyond which localized necking or localized through thickness thinning. Through thickness thinning is nothing but necking. Through thickness thinning means epsilon 3. Epsilon 3. Okay, whatever we discussed until now, it is nothing but epsilon 3. This epsilon 3 is very important. It should not go beyond a particular limit. So otherwise necking will happen. It is also called as necking. And subsequent fracture occur during the forming of a metallic sheet. Okay, so it will show the strain levels. So this forming limit curve can be shown in this way. Okay, the same figure which I have shown before, but I just shown in a different way. So you can see that you can have different betas 1, 2, 3, 4, 5, 6, 7. I just indicated different stars to get the limit strains, and you can see that these all are deformed and different strain paths. Let us say it is going to be linear. Let us assume that way. And then all the strain values below this curve are actually safe, and once you reach this curve, you are actually in the onset of necking, and above that definitely sheet is going to fail. So that is the meaning. This is called the forming limit curve. So the next important definition is called as a forming limit diagram. It is called as forming FLD in short. Okay, it's a graph in which experimentally measured major strain, okay, and minor strain combinations are plotted to develop FLC. So basically epsilon 1 star and epsilon 2 star, we call it as limit strains, isn't it? So you want to get that practically, experimentally, then there are certain procedures. Okay, while doing that you have to calculate some strains. Okay, so it is a graph in which experimentally measured major strain, minor strain are plotted in one graph, and there is a procedure to develop forming limit curve. So that entire diagram is called as forming limit diagram. Okay, for example, I have shown forming limit diagram here and forming limit curve here. Both have similar meaning only. Only thing is like this forming limit diagram will include some strain values, okay, which will be separated by this forming limit curve in this fashion. You can see that these are all, these orange ones, circle ones, this diamond shape, okay, both are shown here. The orange ones are actually safe strains and these red ones, diamond ones, are basically failed strains. That's why I said fail and safe. Okay, and you can see that this curve is actually separating these two data points, these two sets of data points. Okay, so probably these data points were obtained from one strain path, this is from another strain path, and this is from plane strain path, this is from another strain path, this set will be from beta is equal to 1. So you are going to deform the sheet and you are going to get both safe strains and failed strains and plot all in one, okay, to get a curve which is going to separate these two. So if you plot all the strain values inside this diagram along with forming limit curve, then you call this as forming limit diagram. So that's the main difference here. So forming limit diagram is nothing but forming limit curve plus strain values used to separate these two. Okay, so strain values used to construct forming limit curve. So then there are three important modes of deformation. We have already seen 5 different modes, but biaxial stretching, we know that. What do you mean by biaxial stretching? It's a mode of deformation in which positive strains, both are positive, epsilon 1 and 2, both the principal strains are positive, are observed in both in-plane directions at a given location or a grid location. Okay, so biaxial stretching means epsilon 1 and 2 would be both positive. Say for example, epsilon 1 and 2 both will be positive means all this red or it could be yellow one, all are on this side of the diagram or nothing but your biaxial stretching. One case is balanced biaxial stretching where epsilon 1 and 2 are same. So which will give you epsilon 2 by 1 as beta is equal to 1, which will be probably an extreme case here. Okay, so deep drawing mode of deformation also we have seen. Okay, is a mode of deformation in which strains on the test specimen surface are positive in direction 1. That is epsilon 1 is positive. It is always going to be positive only. That's why you have only one y-axis. Epsilon 1 is positive, but epsilon 2 can be negative. Okay, epsilon 2 can be negative. Okay, and the negative in 90-degree direction, that means along direction 2, which is epsilon 2. So epsilon 2 is actually going to be negative in this case, so that this drawing strain path is going to be on the second quadrant. Plane strain mode of deformation is also we know already. Okay, it's a mode of deformation or forming that maintains near 0 minus strain or 0 minus strain. So epsilon 2 is 0. Suppose epsilon 2 is 0 means this point, this entire y-axis. So you have any limit strain in y-axis, say for example this point or this red point or this orange points, they are actually closer to plane strain. Okay, so in this case you will see that there is a positive major strain and it's going to be 0 minus strain. Okay, it's going to be 0 minus strain. So minus strain is positive in this side, minus strain is 0 on this side, minus strain is negative in this side. Biaxial stretching, plane strain, deep drawing mode of deformation. So when we speak about forming limit curve, there is one important level in forming limit curve, one important data in the forming limit curve. Okay, that generally we take it as a reference, that is called FLD0. So FLD0 is nothing but this particular point. Okay, it is a location on forming limit curve or this particular star. The star we say here in plane strain, that is nothing but your FLD0. Okay, that is nothing but your FLD0. So you can call this as, I will write this as FLD0 like this. It's a location on the forming limit curve that has got the lowest major strain or the limit strain in plane strain mode, or the limit strain in plane strain mode is this point. When you go along y-axis, you are going along plane strain mode of deformation, and you will see that whatever limit strain you have, that you can call it as FLD0, and that is actually a conservative window for forming sheets. So when you deform a material along plane strain mode of deformation along this, you will reach the forming limit curve at the earliest as compared to any other strain path, any other beta. So you are deforming along a conservative window to reach the limit strains little early as compared to the other two extreme strain paths. Okay, so these all are actually drawn schematically here. So you see that this is the initial circle grid pattern we have in the sheet. Let us say there are several such circles you can put. The circles could be of, let us say, as small as 2.5 mm. Sometimes for easy measurement you can have 10 mm also, but smaller the circle, we can get accurate strain values at different locations in a sheet. Okay, so we can imagine that there is a particular L0 and W0. Of course, you can say D0 also. We have already seen this D0. Okay, so I am just mentioning it as L0 and W0, and you will see that in a drawing type of deformation. So it is going to be the circle is going to become an ellipse. Circle is going to become an ellipse with W width, and length is going to increase to this red color one. The red color ones are actually deformed circles. The black ones are the original circle, undeformed ones. Okay. So in deep drawing you will see that it is going inside. So if you calculate along, let us say this is 2 direction and this is 1 direction. If you calculate strain along 2 direction, so naturally it will come somewhere here. So in plane strain mode of deformation you will see that, so this dimension is almost same. So when you calculate epsilon 2 here, so since the diameter is, W naught is going to be same as that of W, so your strain will be 0, but you will have some strain in the one direction. So that will be somewhere here, let us say. And biaxial stretching, you know that circle will become a larger circle, and from this W, from this L you can get strains. W naught, L naught is known, so you can get strains, and you will see that you are going to have some data in the positive side. Okay. So FLC, FLD, biaxial, deep drawing mode of the plane strain, and FLD0, these are all certain terms that is generally used with respect to forming limit curve. So now let us go to one simple test procedure. This test procedure is actually meant for hemispherical dome test or limit dome height test, you can say. And this is schematic is one standard dimensions one can fabricate in a lab, and you can use it to get the forming limit curve or formability of the sheet. So if you closely look at it, the tools are conventional in nature. Say for example, you have a punch which has got a hemispherical bottom, okay, and you have the radius of about 50.8 mm. Okay, and you will see that this hatched one is actually a sheet which is partially deformed, partially stretched, you can say, and you will see that to start with, the sheet is actually going to be flat. It's a flat sheet like this. It's a flat sheet like this, and punch will be touching the sheet in this fashion to start with, and you are displacing the punch in this direction, and displacement is provided to punch in this direction. So and the sheet is actually stretched, and you will see that to avoid the radial movement of your sheet, the sheet is actually locked here by something called as lock bead or draw bead. Okay, and this is actually called a hold down ring, or you can also say blank holder, and there is a die. Okay, all are circular in nature. Okay, so it's a cylindrical punch. Okay, this blank holder is nothing but a ring. Okay, with a hole at the center. Similarly, die is also, it has got a hole at the center. Of course, here it is shown very sharp, but actually there is a corner, die corner. Okay, and your blank holder also has got a typical corner radius like this, and you will see that the gap between the die inner walls is about 105.7 mm, and you can see the lock bead is spaced at about 132.6 mm. Now it's a circular one, so which means that the sheet is actually clamped circumferentially. That's why it is written the circumferential clamping force is applied using draw bead as well as some blank holding force. Okay, this draw bead if you use, it will avoid the radial movement of the sheet, and hence the sheet is going to stretch below the punch. Okay, so I have also given here this LDH test setup showing tools, sheet, and important dimensions. Okay, so the point here is there are some machines already available. Okay, or you can install this machine in your UTM. Okay, or you can use a double action hydraulic press where this type of tools can be installed. Okay, so if there are some already available machines, means the machines are meant only for this kind of experiments. Double action hydraulic press means it's a general purpose double action hydraulic press. So one action is to hold the sheet using blank holder, and then a punch will come separately. That's the second action. Okay, and then the sheet will be deformed. Or sometimes what we do is, if I make this setup and the clamping is actually done mechanically using fastener. Okay, using fasteners you can mechanically clamp the sheet, and this punch is actually held in the UTM, and like any other test, your the movement of punch is actually controlled by hydraulic means, and it will come and deform the sheet. Only thing is, in mechanical clamping you have to make sure that the sheet is actually not drawing. Okay, so I have also said that the contact surfaces of the raw undeformed sheet and punch are actually lubricated. Okay, the sheet is securely clamped in the flange region using a lock bead or a draw bead here, located in the die blank holder arrangement, for the hemispherical punch and hydraulic bulge test. Hydraulic bulge test, what is it, we will see separately. Okay, but for hemispherical punch test and or limit dome height test, this is what you do. So now what we are going to do is we are going to stretch the central area of the sheet. That means the sheet below the punch, okay, is performed without interrupting the test. You should not stop the test. You continue the test, okay, and you are going to do that until necking occurs or fracture occurs. It all depends on how do you identify that. Okay, a series of test samples with grid patterns is prepared with the different widths but with constant length suitable for clamping. So now, in order to get the forming limit curve, okay, you need to deform this particular sheet at different strain paths or beta values, right? That is done in this test just by changing the sheet width. I will show you that just by changing the sheet width, okay, keeping the length constant, okay, and you use this setup to form the sheet until fracture, until necking, and you measure the strain grids in the near the neck region, okay, you will get the forming limit curve. So basically a series of strips of one particular material with the different widths but a constant length will be deformed using this setup to get the forming limit curve. Okay, so that's why in this diagram, if you see, okay, I mentioned 1, 2, 3, 4, 5, 6, 7. So which means that you can use 7 different widths. Okay, you can also use any in between widths also. If you want to get accurate forming limit curve, in between some widths also one can get forming limit curve. Okay, one can get limit strains, but let us say about the 7 different widths can be changed to get the forming limit strains in that particular strain path, keeping the length constant, but length of the sheet should be such that you will be able to clamp it properly here. Okay, you should be able to clamp it. So that's why length is remaining constant, width can change. Okay, so if you see this from the top view, whatever I mentioned will look like this. Whatever I mentioned will look like this. Okay, this is just a schematic I mentioned. Okay, there are 2 things here. One is this light blue, which is nothing but your sheet. I have written sheet here. This is also a sheet. This is also a sheet. This the circular one is actually a punch, the same punch. Okay, this same punch which you see from the top view. You see from the top view, the punch will look like the red color circle, let us say, and the sheets are of this particular length, which are actually same length. You can see, okay, all the 3 sheets are of same length, but width is changing. You can see this W is changed, this W is changed as compared to this. Okay, the width is different in all the 3 cases. I just shown 3 cases as an example. So if you see from the top view, how does it look like is in one case, okay, if you want to get limit strain in the negative minus strain region, that is in the second quadrant to start with, that is in the second quadrant. Suppose in this quadrant, okay, if you want limit strain, so what you need to do is you need to have a sheet of width slightly smaller than the punch diameter. Okay, so negative minus strain obtained from narrow strip test specimens with respect to punch. Okay. On the other hand, if you want to get positive minus strain, then this would be suitable. That means your limit strains will be somewhere here in this portion. If you want that, okay, so then you use this type of sheet. The sheet is actually pretty large as compared to the punch dimension. But if you want plain strain, you pick up an in-between width, which is say for example width is almost same as that of your punch diameter, okay, or maybe slightly lesser than this, slightly lesser than the punch but larger than this, or slightly larger than the punch but lesser than this sheet. That is also available. Okay, so if you deform that sheet up to fracture, then you will get limit strains in the zero minus strain, that is plain strain type of deformation. Okay, so in between these two you may have some width. Let us say 2 different widths you assume. In between these 2 you assume 2 different widths. So naturally if you deform it up to fracture, you will get limit strains in this many number of strain paths. So 1, 2, 3, 4, 5, 6, 7 different strain paths you can get. Okay, and since you are seeing the top view of that, just for a feel, you will see that the draw bead is actually clamped. The draw bead is used to clamp the sheet somewhere here. You can imagine. Draw bead is used to clamp the sheet somewhere here. Okay. The sheet is actually, this is this one. So naturally this will be, draw bead will be clamped fully like this. The top view will be more clear here. So draw bead is a circular ring, no? So you will be, sheet will be clamped fully in this blue region. Okay, now punch will deform it and only this part of the sheet is going to deform. Okay, this part of the sheet will not be allowed to draw in. Same as that of here. This sheet will not go inside. This will be arrested. Okay, so that is the whole idea of this particular test. So now what we do, the punch displacement is stopped when a localized necking. When a localized necking is visible. Okay, when localized necking is visible. Maybe you can put a camera, below the sheet and you can find out where necking is going to happen. If it is in UTM, then you can easily visualize it. If it is other press, hydraulic press, industry type press, then one can put a camera and find out. Sometimes what we do is like you can also get load displacement graph during this testing. Okay, like our tensile test. No, here also you can get load displacement graph and you can see that there will be some failure. Okay, so probably close to that you have to be very careful that necking might have happened. Just before that you should have stopped the test by that time. Okay, so if the test is not stopped as soon as test specimen. Okay, so if the test is not stopped, it can be stopped when fracture happens. That is also possible. Okay, so generally if the sheet preparation is good, okay, if the sample preparation is good without any burr or other defects, it will not split across the nose of the punch. Okay, instead when the punch is displayed beyond the sheet forming limit, neck or fracture occurs in a ring encircling the round cap of the formed region. So what is the point here is like if the sheet preparation is good, then it will not fail in the unwanted region. Like in tensile test, you want fracture to happen, necking to happen in the gauge region. Similarly, here also you want the fracture to happen somewhere in the deforming region, here or here or here, okay, in the sheet or here, okay, in the sheet. If the sheet preparation is good, then this problem will be sorted out. If it is bad, then it can fail in the gripping region also. Somewhere in this edge region it can fail, especially this is a problem in plane strain mode of deformation. So it can fail somewhere in the edge region. Okay, so one has to be a little bit careful in that. So there are some important points with respect to lubrication. So you will see that lubrication improves sliding of sheet over the punch surface and causes material fracture closer to the nose of the punch. Nose of the punch means what we are saying is you may when you do experiments you will find out that generally if you go for dry lubrication, generally your fracture is going to happen away from the center. Okay, it may happen somewhere here or maybe here. Okay, maybe here or here. Okay, but if you are having lubricants or good lubrication is done, generally it moves closer to the punch nose. Okay, so fracture will happen somewhere here. So we are saying that lubrication provides sliding of sheet over the punch surface and causes material fracture closer to the punch nose. Okay, it is, but one thing we have to be very clear that it is important to note that this does not change the forming limit. Generally it is understood that if you put lubricant or you don't put lubricant, you deform the sheet in dry condition, forming limit will not change. Your forming limit curve is not going to change. This forming limit curve which we mentioned just before, okay, this forming limit curve is not going to change, okay, when you use lubricant or you do the test without lubricant. That is why we call it as a material property. But what it does is, it does not change the forming limit as the minor strain epsilon 2 adjusts to the increased major strain. If you put lubricant, the strain value can change, but accordingly epsilon 2 will get adjusted for whatever the value of epsilon 1 you have, which also means that it indicates change in strain path or strain ratio beta are not forming limit strains, actually epsilon 1 star and 2 star. That will not change. Rather what will happen is it will change the route of getting into the forming limit curve. Okay, so it also means that if you put lubricant, okay, so if you don't put lubricant, probably you will reach the forming limit curve somewhere here. Okay, if you put lubricant, it will reach the forming limit curve in some other location, maybe somewhere here, but the forming limit curve will remain same. Forming limit curve will remain same. So instead of reaching a forming limit curve here, it will reach a forming limit curve here, but forming limit curve will remain same. Only thing is there will be slight change in the limit strain values. So that's why it is said that these two strains will get adjusted as a minor strain epsilon 2 adjusts to the increased major strain, but it will reach the same forming limit curve of that particular material. So now, so what did you do? So now the step is basically we have done our test up to this particular point. The punch displacement is stopped when the localized necking is actually witnessed, when it is visible. Now you have stopped it. Okay, so now you have to measure strain and then you have to develop forming limit curve. This is very, very important because your strain measurement has to be accurate so that your forming limit curve is also going to be accurate. If there is approximation in strain evaluation, then there will be problem in the forming limit curve. That is why we said that in a sheet it's better to have circles of the order of, let us say, 2.5 mm diameter or 2 mm diameter rather than 10 mm diameter. Okay. So because 10 mm diameter itself covers a large region, okay, 2.5 mm, 2 mm would be good, so that you can measure strains at a localized locations. Anyway, so now you have to measure epsilon 1 and 2, right? Epsilon 1 and 2 of the individual deformed grids on the sheet surface are measured near the neck of all the test specimens for the series, and it is recorded. So we said that this many number of sheets, no? So 1, 2, 3, 4, 5, 6, 7, right? So these many widths are deformed to get one forming limit curve for one material, isn't it? So we have to measure epsilon 1 and 2 near the neck in all these 7 different strain paths. So how do you calculate it? You know that epsilon 1 is nothing but ln of L by L naught. Ln of L by L naught, isn't it? So ln of L by L naught is with respect to this. Okay, ln of L by L naught. Okay, ln of L by L naught will give you epsilon 1, and epsilon 2 would be nothing but ln of W by W naught. We have already done a lot of problems in this. We know how to calculate it. Okay. So one can also look into this ASTM standards. Okay, this ASTM standard is the standard test method for determining forming limit curves. You can look into it. There's a lot of details available in that. So now when you are measuring this limit strains, you can use a microscope with suitable magnification. Okay. So and the only thing is, like, now this is a curved bent. This is a bent sheet, isn't it? So you will see that the sheet is actually bent. Okay. The deformation is actually out of plane. This type of test is a deformation is called as out of plane type of deformation. And suppose you want to measure a grid here on the surface. So what you need to do is you focus your microscope perpendicular to this. You have to see like this. Okay, you have to orient your sheet in that fashion to get the actual dimension rather than the projected ones. Okay, so you have to use appropriate magnification so that you can see that neck strains properly. And there are a lot of facilities now. You can take photo of a few grids around the neck region, and you can process it later also. Okay, and it is also said from the ASTM standard, the epsilon 1 and 2 shall be accurate to about 2.5% strain. You have to convert into 100. To 100, if you put into 100, it will be in percentage. Okay, so we have to have an accuracy of plus or minus 2.5% strain. Okay, that's what is mentioned in ASTM standards. Okay, and now when you are measuring this, strain data points, you have to actually categorize that into 3 different data points. Okay, one is the safe. Safe one means no necking. It is safe. It is little away from the neck region. It is little away from the neck region. And marginal, localized necking. This is what actually we want. Marginal ones. Marginal one means localized necking very close to the neck, which you are going to measure. And then fracture region. Fracture region means these are regions which are much beyond your localized necking. Okay, these 3 strains have to be separated out clearly. This one and this one are very important actually, because we have to stop the test. We have to measure forming limit strains when it is necking. Okay. So what you do is, so you have to measure this epsilon 1 and 2 in all that 7 different widths, for example, and you have to categorize that into probably these 2 important categories, safe and marginal. So as I showed you before, in this particular data point, you can say that these red data points are failed, and this orange data points, I said these are safe, right? So you can say that this, instead of failed, you can say that these are all localized strains. Okay, marginal ones. Okay, very close to the forming limit curve, very close to the forming limit curve, but it is marginal. It is just locally necked, whereas orange ones are fully safe, little away from the neck region. Both the strains have to be measured in all the strain paths. And all such data, suppose 7 different betas you have, that means 7 different widths you have. Okay, suppose in each strain path, each width, you are measuring, let us say, 10 different data points. Okay, the 10 different data points, okay, 10 different data points has got 5 plus 5. Let us say 5 in safe and 5 in, let us say, this localized neck. Local neck. Okay, 10 different data points. So this 5 plus 5, 10 into 7, 70 data points have to be plotted in one graph, clearly distinguishing between different strain paths and this 5 and this 5. This has to be separately shown. Okay, specifically the safe and local neck data points 5 plus 5 in each strain path have to be separately shown. Maybe the way I have shown could be one example. So one is in a red color, other one is in orange color, something like that. Okay. And then what you do is all the data points are coded in FLC as safe and marginal, and you have to draw forming limit curve. Okay. Physically you have to draw a forming limit curve. FLC is drawn by drawing a curve. You have to draw a curve on the FLD. Okay, you have plotted all the strain values now in the FLD based on the following points. How do you do? Draw a smooth curve above the largest safe epsilon 1 strains. Okay, so with respect to this diagram, if you see the largest epsilon 1 strain, or these are the values. Let us say 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11. These are the largest in epsilon 1 strains. Okay, you have to draw a curve just above that. You have to draw a curve just above that. Draw a smooth curve above the largest safe epsilon 1 strains along with associated epsilon 2 strain. So you have to draw a curve like that, such that all these largest safe strains are below the curve. Okay, it may so happen that some safe no localized necking strain points are intermixed with marginal. Okay, intermixed with marginal localized necking points. If that is the case, draw FLC below these marginal points. Okay, draw FLC below this. Suppose there could be a small localized small band. Okay, where this marginal ones, that means your necked ones and safe ones, can be intermixed. Okay, they are plotted together, they are nearby in this diagram, forming limit diagram. Then at that time also you have to be careful that okay, then you draw FLC below the marginal points. That means none of the marginal points should come below the forming limit curve. Okay. Otherwise, what you need to do is in that particular strain paths, you do more tests, more trials to get more data, so that you can get an accurate, better separation between the failed ones and the marginal ones. So that's the way you have to draw forming limit curve. Finally, you will see that you will get this particular type of diagram. This is called a forming limit diagram. These many issues are there when you draw forming limit curve of a material. So some important information about your test specimens and grid pattern. So what we can do is the longer dimension in the strain paths could be along the rolling direction of the sheet, that one can maintain. Okay, and in the LDS test, whichever we have discussed right now, the test specimen shall be sufficiently long to have secure clamping by blank holder and die without excessive pulling. That I already explained you. So several sets of test specimens are required to obtain sufficient, repeatable, accurate data or limit strains. So one set of 7 sheets may not be sufficient. You may have to use the second set or third set also, and then you may get 70 into 3, almost about 210 data points. Okay, out of that, half of that would be safe, half of that would be localized neck strains. Okay, this much data if you get, you will get a nice, continuous, accurate, it should be repeatable forming limit curve. Okay, so a typical sheet size is given here. For example, if you use a punch of 100 mm diameter, we have used 50 mm, 50.8 mm I said, isn't it? 50.8, isn't it? Yeah. So if you use a punch of 100 mm diameter, okay, I have shown this is a radius, 50.8 mm radius. So if you use 100 mm diameter, we will have a sheet width ranging from 12 mm to 200 mm. That means the negative minus strain will have 12 mm width and the positive minus strain will be about 200 mm in width at the increments of 25 mm, you can say. So that many number of widths you can use. So you have to cut the sheet before test. You have to cut the sheet by shearing machine without any bar. Okay, edge effect is going to be important. Otherwise, it may fail in the gripping region itself. You have to be a little bit careful, and any unsafe handling is also prevented if you use a proper shearing machine, and you may have to polish it at the edge before deforming it. So edge preparation is actually very, very crucial. Here on the grid patterns, okay, so let us say this is your sheet. This is your sheet. Okay, so this is the best one. Generally, people use this circle grids. Okay, the circle grids could be connected to each other, next to next. I just drawn with some gap, but otherwise this can be little bit touching each other. Like this, you have to put several grids on the sheet surface. 200 mm width and 200 mm length. Okay, you can imagine a square sheet of 200 mm width and 200 mm length, right? In that you may have to put this all circle grids very close to each other. You can imagine this is about 2.5 mm diameter circle grid. You can imagine so many circles will come. I just shown a schematic here. So you can also, people use dot pattern instead of circle, you can print dots. Sometimes squares are also used, or connected square. Sometimes a combination can be used. So a square and a circle combination also people use it, but this is predominantly used and easy to measure also. So when you deform a square, it becomes some distorted dimensions, isn't it? So whereas the advantage of using a square circle grids is basically it's going to become either circle or an ellipse. So it's easy to measure strains. But these are all different grids available. One can look into ASTM standards for more details. This is another dimension just I gave you, that instead of rectangular samples and square samples, sometimes people use this type of samples also. The edges are curved in nature. This is also LDH sample only, but sheet samples with a curved edge instead of straight edge. This is also used sometimes. You can see that this is 20 mm width, the negative major strain, and probably your 60 or 80 would have would give you plane strain type of deformation. 40 and 60 are in between. 120 would give biaxial stretching, and 220 would be your balanced biaxial stretching. You can imagine your 100 mm diameter punch superimposed above this, the top view. How does it look like? Okay. So, and some of the deformed sheets are shown here, photographs is shown here, just for your information. And you can see that there is a small neck here, you can see, and you have to measure strain closer to the neck to get the forming limit strain. Okay. So anyway, let us go ahead to the other formability tests in general. Okay, this formability test in general, okay, are classified into two types. One is intrinsic test, other one is simulative test. So intrinsic tests, okay, there are some categories here. We will discuss one after another. Uniaxial tensile test, we know that. Plane strain tensile test, Marciniak stretching, sheet torsion tests are available. Hydraulic bulge test, I was introducing that before. Miyachi shear test, hardness tests are also there. Okay. These intrinsic tests actually assess the fundamental features of materials that are relevant to their formability. Okay. So the type of test itself will tell you what is it actually. Okay. These are the tests which will give you mostly your type of like stress strain behavior, your forming limit, like that, which are actually material property type. Simulative test, in simulations the material is subject to deformation that closely approaches distortion that would occur during any certain forming procedure. Say for example, you have bending, stretching, drawing, stretch drawing. These are all some tests which are of simulative nature. So you want to simulate this type of actual deformation at lab scale. So how do you do that test? So bending is a separate test, stretching separate one, deep drawing or cup drawing separate one. You want to combine stretching and drawing as stretch draw test, another one. Buckling tests are available. We will see some example. These are all other tests available. So we will see one by one.